All right, so we just had an opportunity to go through and we looked at differentiability in regards to just solving for a problem with two variables. And in that, what I wanted you, so just to show you the question we're talking about, this is in the notes that we took today, talking about finding A and B so that's differentiable everywhere. And I use that word differentiable without really defining it and mentioning what it is. And all I told you was that the derivative exists. And when we did that, we found out we had to have f prime to find that a and b, which let us use some limits on the derivative. But then we also did a continuity piece of work. So an interesting thing is that, I had to pause it, so it's going to be kind of weird. Sorry for the stop. So an interesting thing is that this continuity thing that's in there is going to be really important for the concept of differentiability. So as you can see, it says it is differentiable, or that the derivatives exist at x equals c. So we're talking about specific points. If the derivative f exists at x equals c, in order for the derivative to exist at x equals c, the graph of f must have local linearity there. So local linearity is when we zoom in on a graph and it starts to make a line. And this can be seen if we look at the two different graphs. One's going to be differentiable, one that's not. So if we look at the graph x, absolute value of x minus 3 plus 1 versus x squared. So let's start off with, oops, that's not what I wanted at all. There we go. Let's look at the graph of x squared real quick. This is a definition of something that is differentiable. So I look at the graph. Oops, that's not very useful at all. Zoom in. I want to zoom in at the standard window. Normal graph. We're used to seeing that. Let's go to x is. I want to go to x is 2. Boom. So we're at that spot. What I'm going to do is I'm going to zoom in on that spot. That's clearly a curve. As I zoom in, you'll see, yeah, that's definitely a curve. We keep zooming in. I don't know why I did that. So I zoom in a little bit closer and we see, well, it's still a curve. Okay, well, watch, I'm going to zoom over a little bit. And you'll notice that the curve keeps looking like it's maybe flattening out a little bit until I finally zoom in ridiculously close, and you can see that the graph now looks like a line. Now remember, this is y equals x squared. It doesn't look like that. So that is the idea of local linearity. If I zoom in really, really, really tight, it looks like a line. Contrast that to the absolute value function. Specifically, at the part on the absolute value function, where we hit the vertex right down here. If I were to zoom in on that spot, so I'm going to move over there, I zoom in, whoops, 3, on that spot. Oops, I don't think I zoomed in. I think I zoomed out. Let me zoom in. There we go. If I zoom in on that spot, no matter how tight I zoom in on this location, the graph will always look like a V. Shouldn't be a surprise. That's kind of what we expect. In fact, let's take a look at the window. You know, that's a whole whopping 0.1 away, not even. So it's a really zoomed in, really, really tight window, but it still looks like a V. That's not linearly local. Mathematically, graphically, what that looks like is one of two situations. So there are three different ways that we could have. 4 different ways, my apologies, that we could have something that is not, realize what I'm saying, not differentiable. All right? The 2 here are that we could have what's called a sharp turn. If I zoom in on this spot right here, that will always look like a V. So if we zoom in on that spot, that looks like a V. If I look at a spot with a discontinuity, you'll notice if I zoom in, you would get nothing there. That's going to be another part that is really important. This discontinuity thing. In fact, I want you to star that. That's really important. So anytime there's an asymptote or a discontinuity, realize this would also be true for holes and jumps. We also have the vertical tangent line. Vertical tangent line is probably the most basic aspect of this, at this particular point when x is equal to 1, we'll see that at a vertical tangent line, by definition, a vertical tangent implies undefined slope. And since the derivative is the slope of a tangent line, that would not exist. Finally, a cusp. If you imagine zooming in on this portion, you can imagine it kind of starts looking like one of those little birdies. If you start drawing a bunch of them, you got yourself a flock of seagulls. In this case, at x equals 1, we would get what's called a cusp. Now, before you get too scared about me being picky about these two are essentially the same exact concept, and those words can be used interchangeably. Now, I mentioned something about continuity. Differentiability is going to imply continuity. If there's a hole, a jump, an asymptote, you cannot be differentiable because you're already not continuous. However, this is a if-then statement. This is not an if and only if, which means differentiability implies continuity, but continuity does not imply differentiability. So that is going to be a big deal, and it's something that they're going to expect you to know. For instance, if I look at question number 1 here, number 1 says, hey, where is this? If we look at this, this is telling us to find out when it's not continuous in y and when it's not differentiable in y. So if I look at 1, there's an asymptote at x equals 3, so discontinuity at x equals 3, and that is an asymptote. If I look at b, we would say that this is non-differentiable, or non-diff, at x equals 3, but now we're not going to say there's an asymptote. What we're going to say is that there is a discontinuity. So you can see how I'm going to use the fact that there's a hole there to describe that. Question number 2, if I'm telling you that there's a discontinuity, well, I look and all the points look good. The limits look good. So what I would say here is that this is continuous. Meanwhile, if there's non-differentiability, we're looking for any time that there's some weird sharp turn where if I zoomed in on it, it would not look like a line, some sort of line. So if I look at these points, you'll see that there is this sharp turn aspect that comes down and then it goes up, or it comes down and then it goes up really hard. That would be our situation. So we'd say non-diff at x equals plus and minus 3. Now, I do want to mention something with the sharp turn because all of my examples show sharp turns being a negative into a positive. They could be less drastic. So another situation where non-differentiability could be is if the graph just changes like this. That's not a smooth curve. You see how that's an angle? So this is also a sharp turn. We also have a situation where we go like this, and then we come up. That would be another sharp turn right there. So be aware, it could be a positive into a positive. It could be a negative into a negative. As long as there's some form of change that suddenly happens, that's non-differentiable. The reason why is we have to remember that the definition of a derivative is technically the limit as h approaches 0 of the f of x plus h minus the f of x all over h. So if we're looking at a specific point on these graphs, folks, well, the rate of change over on this side is really, really steep, while the rate of change on this side is really shallow. So you can think the rate of changes don't equal each other, so the left limit and the right limit wouldn't be equal. So in a piecewise, like this one, determine if it's continuous or differentiable at the value of the function where the rule changes. Well, the first thing we do is we check for continuity, which requires a point. In this case, the change is going to be at 2, f of 2, which is 4 minus 12 plus 10, or 2. And then we need to find the left limit. So the limit as x approaches 2 from the left, and the limit is x up. X, there we go, approaches 2 from the right of f of x. From the left, that's still going to equal 2, and from the right, we would have 4 minus 2 is 2. So the limit exists, and the point and the limit are the same. So since the limit, x approaches 2 of f of x equals f of 2, we can say continuous at x equals 2. That's all old, So for differentiability, all we do is we say f prime of x now, and we evaluate that. We take the derivative of both sides, 2x minus 6, and negative 1 of x is greater than greater than 2, I apologize. And x is less than 2. I don't want to say equal to yet, because even though there's an equal to here, I haven't proven this. I need to show that the left limit and the right limit are equal before I can actually put an equal to there. So I say x is approaching 2 from the left, limit as x approaches 2 from the right. And now we've got to be careful with our notation, because now we have f primes we're going to sub in. So now we got 2 times 2 minus 6, and I've got negative 1. So I've got negative 2 and negative 1. Since the limit as x approaches 2 of f prime of x does not exist, we claim that this is non-differentiable. This connects down to this. In fact, what I want you to do is, I know I told you I'm not going to really give you homework. I want you to try to answer this particular question down here, what this might look like on the AP test, using this as your example. The question is asking if the function is defined as above, then f prime of 2 is. So I'm asking you, what is the derivative at 2? And I want you to think about what we did in this problem to help you here. Remember, we check. I'm asking for what the derivative is, so you can take the derivative of individual pieces. I will give you an example tomorrow. We'll talk about the questions that might come up from this, and then we'll get some board work done. Hopefully this was not too bad of a crash course, and I look forward to seeing you.